If we continue our discussion about cross product, we've just had this generic description about cross products, which you can find in just about any subject where we talk about vectors with any depth to it. But Steve, why do we care? Why do we care in an engineering statics, engineering mechanics course? Why do we care about cross products? Well, very simple. When I look in three dimensions, the moment about any point, if I just say the moment about the origin, but the moment about any point in space, honestly, is equal to a cross product. It's equal to the cross product of an r vector or a position vector crossed with a force vector. So the magnitude of this moment is going to equal then r, the magnitude of that position vector, times the magnitude of the force, times the sine of the angle between them. And if you look at, if I draw some force F, and we say we've got some position vector r that intersects it. So r is, we'll give it a definition here in a second, but r is essentially any vector that touches the line of action of the force F. You've got an angle theta between them. And notice this is d. This is your perpendicular distance, which is just r sine theta. I'm in the margin there, which I hate doing, but I wanted to try to squeeze that in there. So we've already talked about moments in two dimensions and just simply said that the moment is the force times that perpendicular distance, or the lever arm, if you will, the moment arm. That's what this represents. So what happens then is r can be any position vector from the point of rotation to the line of action of the force F. So that force F, I could draw a position vector all the way out here. Right? So from this same point all the way out here, if we say that this is point O, the origin, if you will, or some point O, and if I say, well, you know what, I'm going to draw a position vector all the way out here. Well, you know what? If it still intersects that line of action, the line in the direction of the force, I can draw R all the way out here. I can draw R right here. Doesn't matter. Does not matter. There are infinitely many R's that will satisfy this equation. That's a bit kind of confusing, I know, but that is how this works. Is any position vector from the point of rotation out to the line of action of the force. And again, theta represents the angle between the vectors, between the line of action of the two vectors. Okay. So what happens then is to find resultant moments, moment resultant about some point O, maybe the origin, then what we're going to do is we're going to sum all of the R vector crossed with force vector that are applied to or about this point O. Anything that's going to cause potential rotation about point O for our object or our structure or a particle, whatever it may be. We're going to add up the result of this position vector crossed with that force vector. Now, how often are we going to work this in three dimensions? Well, it gets kind of a bit tedious because you end up taking R1 crossed with F1 plus R2 crossed with F2 plus R3 crossed with F3 etc. As many forces as you have applied or causing rotation, potentially causing rotation about point O. This is a summation. We add all of them up, meaning we're going to go through some sort of determinant of this 3 by 3 matrix for every single force and a position vector out to it. It's doable. It's not hard. It's not difficult. It is a bit tedious. We'll see, especially in Chapter 5 and beyond, what my preference is if you resolve the forces into their x, y, and z components, then you can take each individual x, y, and z force and determine its individual moment that it's going to cause about a particular axis or a particular point. It's a lot easier to do that. We'll see those examples as we continue on in this material here. But this is why we care. This is kind of where we're potentially headed forward with the rest of the course. Now, remember though, in 2 dimensions, all we have to do is just simply take force times its perpendicular distance and then and preserve the sign, if you will. Which basically means if it's causing a counterclockwise rotation in the xy plane, that means it's positive. And if it's causing a clockwise rotation in the xy plane, it's causing a negative, because what's actually happening, if you're looking at the xy plane, basically the z direction is into the page, basically coming right out at you if you're looking down the xy plane. So to go from x to y, your thumb's going to point in the positive z direction if I'm going counterclockwise. And if I'm going clockwise, that's opening my hand. That's the opposite there. That's actually in the negative z direction if everything's in 2D and everything's in the xy plane. So what do I mean by that? Well, if I'm doing result moment, I'm just going to take force times distance for each force and then add the ones causing counterclockwise and subtract the ones causing clockwise moments. We've seen that already in an example or two, and we'll continue to see that throughout the semester, but just it's worthwhile to mention. This is always true. Now, this is true in 2 dimensions. If you go through and build this matrix where your z components are 0, and you go through mathematically and see what's left out of this when the z components are all 0, well, notice that this term and this term both end up picking up 0 value. Well, actually, you could have several terms. You get this one, this one, this one, and this one all have zeros because they have z components that are 0. So the only things left are this guy in the k direction and this guy in the k direction. So you can do the same thing with a 2-dimensional force, but it's a lot easier to just simply take the force times the distance rather than build the big matrix and find its resultant or determinant. Add the clockwise, subtract the counterclockwise. I've got a pretty simple example. I've got a couple of examples in 3 dimensions here we can work. This is the first one, right? So basically, I'm going to draw this with you, so you got it in your notes, but this is what we're going to draw. We've got this bar of some kind, of terribly drawn, some bar in the xy plane, and a force in the z direction applied right to it. So and we're going to find a couple of moment quantities there. All right, this is L7, page 3 of something, and we're going to do an example. So I'll draw this with you so you got it in your notes. You got X, Y, and Z. And we've got this bar of some kind, essentially in the XY plane. It comes out a little ways and then it juts out a little ways further. So I don't know if I'm going to draw this very well. We'll give it a try. I don't think whenever I drew those initial notes years ago at this point, I think I probably did a better job, but maybe we get the idea. All right, so something like this. I don't know. Maybe that's okay. I've got some bar attached to the origin here. And we're going to apply out here at the very end of this thing a force of 20 newtons. And it's in the negative z direction. Minus 20 newtons in the z direction. 20 newtons going straight down. Now this point, again, it's in the xy plane, so you've got a distance here along the y-axis of 0.4 meters, and then the distance in the x direction is 0.3 meters. So if this is, we call this the origin, and if we call this point A out at the very edge here, right? So the y value for A is going to be 0.4 meters positive, and the x value for A is going to be 0.3 meters. And I don't like when they draw it this way, but this is, I mean, for a statics problem, I don't like that this is where they put the dimensions, but in an engineering drawing, this would be where they would put the dimensions. So you have to be used to taking the information and figuring out, okay, how do I convert that into mathematical useful information? And they're telling you here, well, this distance in the x is 0.3, and this distance here is 0.4. Okay. So what do we do here? If we want to, what are we looking for? That's always our first step. What are we trying to find? First, we're trying to find the moment applied to the origin, the moment vector applied to the origin, and they also want to know what is the moment applied about the y-axis. What is specifically the moment applied about the y-axis? Let's say this thing is threaded right here, and the threads are in the y direction, so we need to know how much force is being applied, or how much torque or moment is being applied about the y-axis to determine how much this thing gets screwed or unscrewed, so to speak. So, well, let's find the moment about the origin. That, of course, is going to be a position vector crossed with F. Now, how do we construct a position vector? Well, this position vector is going to go out to point A, which from the origin to point A, that's actually pretty simple. You're going to take your x value, 3I, plus your y value, and it's 0.3, I apologize, 0.3I plus 0.4J. There's no K component, it's just in the XY planes, and these are both meters. So that's going to be my position vector. And those are both zeros, I apologize, it's not very well written. That's my position vector. My force vector, then we've already written out here, is minus 20 newtons in the z direction. And I need to cross these two vectors together. Okay, so R cross F, the moment about the origin, I prefer the diagonal method. If you like expansion by minors, do it. Whatever method you use to find the determinant of a matrix is not going to bother me. Just be consistent and have something that works. 0.3, 0.4, 0, so the components of the R vector. Components of the force vector, that's 0, 0, and minus 20. And then I do the diagonal method, which means I repeat these values. 0.3, 0.4, 0, 0, 0, minus 20. And I go across and I do some diagonals here. Right, so this diagonal will be 0, this K, the J diagonal is 0, the K diagonal is 0. They all have 0 quantities. This one is not 0, so it's going to be minus 20 times 0.4 I. So moment vector so far is going to equal this, and and make sure you keep track of your units. I'm going to put brackets there so you can see the units. Put the units out here at the very end. All right, and then the negative quantities. So this has a 0. That's got 2 zeros, and this does not have a 0. So these all these diagonals coming back this way are negative. So it's going to be minus this one, minus a 0.3 times a minus 20. So it picks up two negative signs, and that is in the J direction. And these are all Newton meters. So then we just multiply this out. These are, you can pull your calculator out, but I feel pretty comfortable. I can do these in my head. It's 0.8 times 10 is going to be just simply 8. It's going to be minus 8 in the I direction. And this is plus 6 in the J direction. Those are both Newton meters. Now what does this mean? Well, and by the way, this is one answer. What did they ask for? Is that everything? Well, they did want to know the moment, which we just found, and they want to know what is the moment in the y direction. So the moment, the magnitude of the y direction moment is just simply going to be 6 Newton meters. Now what does that mean? Well, that means that about this y-axis right here, I've got a 20 Newton force being applied at with a lever arm, essentially, a perpendicular distance of 0.3 meters. And if you kind of put your thumb in the positive y direction, and notice that this force is trying to close, this 20 Newton force is trying to close my hand. If I put my thumb in the positive y direction, that tells me that's a positive moment being applied about the y-axis. And its distance, of course, is 0.3. So 20 times 0.3, I actually have 6 Newton meters applied in the positive y direction. You can find that mathematically. You can also kind of look at the diagram. If you've got a well-drawn diagram, you can kind of do it by inspection. Either one of those are correct because you get to the same point, and you get to the same point every time. I'm going to stop there. We'll pick up the next one.